Okay, here is a description of a AP Chemistry lab experiment that our group will be doing that deals with chemical kinetics, that is, rates of reaction. I am going to read this in its entirety and occasionally just throw in some little vignettes of useful information if and when they come up. So this is not really required reading. If you want to just read this on your own, it's fine. Okay, here we go. Introduction. When two chemicals react, the reacting molecules or ions must collide. That's collision theory. In order for the reaction to take place. We know that they have to do more than that, right? They have to collide with enough force and at the right location. Okay, reading on. If the reactants are forced to collide more frequently, then the reaction should be faster. Agreed. Two factors which can influence the frequency of the collisions is the temperature and the concentration. I would think higher temperature and higher concentration would lead to a higher frequency of collisions, be they effective or ineffective. Increasing the temperature of the reactants causes them to move faster and thus collide, move more frequently. Yeah, no kidding. If the concentration of a reactants, I guess get rid of the A, of reactants are increased, then there's more opportunities for collision. Yeah, I get that. Some reactions have been measured to occur in extremely short periods of time, as few as femtoseconds to even attoseconds. Ooh, look at those cool prefixes. The purpose of this experiment is to measure the effect of temperature and the concentration and the rate of a specific reaction, the formation of carbon dioxide from an alka seltzer tablet plopped into water. Plop, plop, fizz, fizz. Alka-Seltzer's tablets contain aspirin, that's nice, and sodium bicarbonate, plain old baking soda, and some citric acid. Carbonate and sodium carbonate and bicarbonate compounds react with acids to form carbon dioxide. So regardless of whether it's carbonate or bicarbonate, this happens to be bicarbonate, they would react with acid to form technically they're going to form, this isn't shown, they'll form carbonic acid, H2CO3, which then spontaneously decomposes. You don't really need to know it. Just go directly to the water and the carbon dioxide, which will outgas. And if it's CO3 2-, that would be carbonate. It also forms the same thing. In an Alka-Seltzer tablet, the bicarbonate and acid are solids, and thus the H plus and the CO3 2- are not free to move, collide, and react. I wonder if they keep them apart somehow physically. When plopped into water, the citric acid and the sodium bicarbonate dissolve, and then suddenly they can react. This results in the formation of carbon dioxide, gas, and water. By measuring how fast the carbon dioxide gas is formed, we can measure the rate of the reaction. Okay, that's the real key right there. So given this material, we're going to determine that the volume of carbon dioxide formed is directly proportional to the mass of carbon dioxide formed. I guess that's true. Mass of CO2 formed, interesting. And the mass of the bicarbonate that's decomposed. The volume of the CO2 formed at 10-second time intervals is measured using the apparatus shown on the next page. And there it is. So you've got a water bath, you've got your tablet, you've got a vial of water, and it's sitting right up there. I would think that we could just tip that thing over by shaking it or something. The reaction begins. The gas is forced up to water in a flask, at which point the gas continues to go into a graduated cylinder, and it says pinch here. Okay, let's go ahead and read it. Half fill a water bath at room temperature with tap water. There's your water bath right there. Measure and record the temperature of the water. Fine. Fill the large Erlenmeyer flask, that's this thing, with water, and half fill the graduated cylinder. That's this thing, with water also. So there's water that goes, I think this straw is submerged. Attach the stopper to the large flask as shown above. It's a 2-hole stopper. And leaving the smaller flask stopper free. So this isn't in yet. Place the other hose in the graduated cylinder. There it is. This can be simply a hose. It doesn't have to be like glass. So that the opening remains below the surface of the water. Good. Using a pipette bulb or other device, blow air into the free stopper tube to force water from the large Erlenmeyer flask into the graduated cylinder to create a siphon. There should be no air in the hose that goes from the large flask to the graduated cylinder. If a siphon is successfully established, the water level inside the large flask here can be raised or lower by moving the graduated cylinder above or below the level of the flask. Interesting. So you'll see the seesaw pattern when you move the graduated cylinder liquid level higher or lower. So that should be testable. Allow enough water to siphon into the large flask to essentially fill it. And there it is, essentially filled. Then pinch the water-filled tubing right here with a pinch clamp. So use something to pinch that baby shut. It's full of water. There should be no gas in it to prevent the water from siphoning over. Sounds like at this point you're going to get a change in the level that won't be affected by any kind of gas. Everything's filled with liquid, I believe. Empty the water in the graduated cylinder and reposition the hose into it. Carefully place a vial of water taken from the water bath, and an alka seltzer tablet into the dry 250 milliliter flask. So there's the water that should be the same temperature as the water bath, as long as you operate fairly quickly, I would think. There's your alka seltzer tablet. Now you're going to stick that rubber stopper back on. Put the stopper tightly onto the flask and remove the pinch clamp from the hose there. Otherwise you'll have a closed system. That's not good. A small of water will drain into the cylinder but should not siphon from the flask. If it does, there's a leak. You got to fix it. Hold the 250 milliliter flask in the water bath. That's this little one here. And swirl to start the reaction. Holding the cylinder, so you're going to knock it over, I believe, right? Holding the cylinder below the bench level. That's the graduated cylinder there. Record the volume of the water displaced every 10 seconds. So you're going to get a rate. Somebody's going to count to 10 and you're going to say, 8 milliliters of water or 1 milliliter of water. And somebody shouts it out and you can dial it in, do it for as long as it takes until it's unchanged for 20 seconds. And then you'd just be wasting your time. The most accurate results are obtained by marking the level of the water in the cylinder directly on the cylinder every 10 seconds. Ooh, good idea. Have a Sharpie ready. When gas evolution is over, read and record the volume measurements in your notebook using the markings on the cylinder. Also do trials for a low temperature, that's negative 10 degrees Celsius, and a higher temperature, 30 to 40 degrees Celsius, using cold water or hot water in the water bath and the reaction vessel. It's not negative 10. I was wondering, everything's going to freeze. About 10 degrees and about 30 to 40 degrees. You can measure the precise temperature, but that you want it to be somewhere near that. Be sure to measure and record your reaction temperatures. Analysis. The tables of times and volumes along with the identification of reaction conditions will be in your results section. So we're going to write up a little lab report. Use graph paper to make plots of carbon dioxide volume versus time for your results. Be certain to title each graph and label your axes. Include units. Trials can be plotted on one graph using different colors for each, but use the maximum area possible on your graph paper. Normally a straight line can be drawn from the graph origin through the initial points in each trial. So they're giving you a little hint there. The slope of this line is a measure of the rate of evolution of carbon dioxide. It gives you a reaction rate. It's expressed in units of milliliters of carbon dioxide per second and calculated by dividing the number of milliliters of carbon dioxide collected by the time it took to collect the gas. You should chat about this stuff with your lab partners to make sure you're comfortable with your results. An example is shown below, which has a rate of slope of 2.4 milliliters per second. Unfortunately, we did not include that graph. Tabulate the average rate of the reaction at each of the 3 temperatures for the tablet. These are your results. Please determine the instantaneous rate of the reaction at a time between 10 and 30 seconds. And now plot a graph of the natural log, that's ln, of the carbon dioxide volume versus time, and describe that graph. Finally, suggest a rate law expression for the reactions based on your graphs and information in your textbook. Good luck. And by the way, it's probably easier just to read this thing you've learned by now than to listen to this little explanation. Okay, that's our reaction for kinetics, the kinetics unit.